Okay, we're going to pick up on slide 38, which talks about center of mass or center of gravity. Your center of mass is just the point at which the entire weight of a body may be considered as concentrated so that if supported at that point, the body would remain in equilibrium in any position. So an object that's free to rotate about a pivot point is going to come to rest with the center of gravity directly below that pivot point. Now, if you have a symmetrical object, the center of gravity is going to lie at the geometric center. Okay. Now, interesting thing to note, though, is you don't have to have any mass there for that to be the center of gravity or center of mass. If you have a tennis ball, it's hollow in the inside, but the center of mass is at that geometric center. Okay. You can see in this picture, we have two symmetrical objects. So the center of mass is going to be at the intersection of those two lines that cut it in half. It's that physical center of your object. Now, if your center of gravity, center of mass, lies directly above the pivot point, like you see in this picture on the left, then there's no torque due to the object's weight, and that object, in this case, that ruler, can remain balanced. But now if we look at the picture to the right, if that object is slightly displaced, then that gravitational torque is no longer zero. That center of mass is no longer over that pivot point, so your object will begin to rotate. So, question, where would you expect the center of mass of a donut to be? Well, so here's our donut, pretty much a symmetrical circle, got a hole in the center. Okay, remember, I don't have to have mass to be that location where my center of mass is located. So my donut center of mass is going to be basically right in the center. Now, what if we have a object that's not symmetrical and we want to find the center of mass? Well, that's what this slide is talking about. It's a little harder, but it can still be done. So remember, the weight is considered to act at the center of mass. So what you do if you have an irregularly shaped object, you pick a point like you see in this top picture, and you hang that object, in this case, a crescent wrench, to the point where it's going to swing. When it comes to rest, there's not going to be any net torque on it. So if I draw a vertical line, that you can see how I've extended that black line with the red dotted line, that's where there's no torque, and that's going to be where my center of mass is located, somewhere along that red dotted line. And then I have to do, like shown in this bottom picture, I have to pick a second location, hang it again, and where those two lines are going to intersect, you can see here, is going to be their center of mass, right where those two lines intersect. Now, in terms of stability, we can look and see when our rotating object might tip over. Now, notice this is a car. We have our base of support, which we also call our track width, that's between our tires. So our center of mass is right in the center of that. So stable position. Now, if we start to pivot, gravity is going to bring the car back down as long as that center of mass is still over the base of support. We get to our third picture and we're approaching that critical angle where we're now directly over our pivot point. So in that case, if we go a little more, the car is going to roll. As long as our angle's less than that critical angle, it'll come back. And then our final picture, notice now our center of mass is outside our base of support. So that's our unstable position. There's no coming back if your car is that far over. You will roll. Okay, and that's why sometimes you might see and wonder, well, I wonder why this car rolled and that one didn't. It's because of that center of mass being within the base of support or being outside of that base of support. Now, the most stable arrangement is going to be when your center of mass is below the support. So you can see in this picture, our center of mass, where it's located, indicated by the X, and it goes back and forth, okay? But it always returns to its original position. And that's a situation that's known as stable equilibrium. We also have to consider our rotational kinetic energy. Just like we had linear kinetic energy that wasn't a vector, we have rotational kinetic energy that's also not a vector. The rotational kinetic energy is going to depend upon the rotational inertia and the square of our rotational speed. Our units are still going to be joules, so this would be our formula for our rotational kinetic energy, 1/2 I omega squared. Okay, let's look at a couple problems. So in this first problem, we're given the moment of inertia to be 0.040 kilograms meter square. And we're told it's rotating once every 4 seconds. So basically, our omega is 1 revolution every 4 seconds. Okay, we want to put that into radians, which is 2 pi radians is 1 revolution, and that's going to give us 1.57 radians per second. So our kinetic energy, remember, it's 1/2 I omega squared. So we're going to have 1/2 times 0.040 kilograms meter squared times 1.57 radians per second, and that's all squared. So our kinetic energy, when you punch that in, is going to come out to be 0.049 joules. Radians do not go into your final units, okay? So now we're able to calculate our rotational kinetic energy, and we were given our moment of inertia. Okay, let's try another problem. So in this one, you're asked to calculate rotational kinetic energy. You're told that omega equals 7.29 times 10 to the minus 5 radians per second. You're told moment of inertia is 8.04 times 10 to the 37 kilograms meter squared. So remember, our kinetic energy is 1/2 I omega squared. So we have 1/2 times 8.04 times 10 to the 37 kilograms meter squared times 7.29 times 10 to the minus 5 radians per second. And that will give us a kinetic energy of 2.14 times 10 to 29 joules. Okay. In our next sample problem. We have a 1.2 kilogram bicycle wheel. So we know our mass is 1.2 kilograms. It has a radius of 70 centimeters, spokes of negligible weight. It starts from rest, so we know omega initial is 0, receives a constant angular acceleration, so alpha is 3 radians per second squared, and you're asked to find the rotational kinetic energy. So we're looking for kinetic energy after a time of 4 seconds. Okay. So we don't know what our final speed is. We're told that it's a wheel. So our moment of inertia is going to be mr squared. So we have 1.2 kilograms times, here again, we have 70 centimeters and we need it to be meters. So that's 0.70 meters. So we can multiply that by 0.70 meters, and that's squared. So our moment of inertia comes out to be 0.588 kilograms meters squared. Now, it is telling us that it is a constant angular acceleration. So we know we have kinematic equations. So we need to find our omega F. So our omega F is going to be omega initial plus alpha delta t. So we have 0 plus, we're given our alpha to be 3 radians per second squared. And we're told our time, we're given to be 4 seconds. So therefore, omega F comes out to be 12 radians per second. So now we can determine kinetic energy, because that is 1/2 I omega squared. So we have 1/2 times 0.588 kilograms meters squared times our omega, which is 12 radians per second, and that's all squared. So our kinetic energy comes out to be 42.3 joules. And let's do another problem. In this one, we have a grinding disc that has a mass of 7.24 kilograms, and it's rotating at 400 RPMs. So omega equals 400 RPMs. Okay, and we know that's revolutions per minute. So we need to go to seconds. So again, just 1 minute is 60 seconds. So we're going to get 6.67 revolutions per second. And then we want to go to radians, which 2 pi radians is 1 revolution. So we have 41.9 radians per second. And normally you'll want to go to radians. It's a more current measurement. It basically is the same as revolutions in that, they're both rotational quantities, but more likely you're going to want to use radians per second. So we want to know, we're told it has a kinetic energy of 74.3 Newton meters. And we want to know what's that moment of inertia. Okay. Well, remember our kinetic energy is 1/2 I omega squared. Okay. I know my kinetic energy. I know my omega. So I can solve this for I. So therefore, my I is simply going to be 2 times my kinetic energy over omega squared. So I'm going to have 2 times 74.3 Newton meters divided by 41.9 radians per second. And that's going to come out to 0.085 kilograms meters squared. Okay. Another thing we wanted to find was the radius. Okay. So it tells me it's a grinding disc. So I look up and I get my moment of inertia is 1/2 mr squared. So I solve this. I'm going to wind up with r squared equals 2I over m. And then I just want r. So r is going to be the square root of 2I over m. So then r will be the square root of 2. I calculated my moment of inertia, 0.085 kilograms meters squared, divided by my mass, which was 7.24 kilograms. I take the square root of that, and R is going to be 0.153 meters. And next thing we want to discuss is our angular momentum. And our angular momentum is going to occur when we have an object that is orbiting a point. Is going to have that rotational quantity that's different from our linear. So our angular momentum is represented by a capital L. It's equal to the linear momentum multiplied by the radius of that circular path. So angular momentum equals L, which equals mvr. Now, a spinning object will also have an angular momentum because you just have a bunch of small particles that revolve around the same axis. So the total angular momentum of that spinning object is the sum of the individual angular momenta of the individual particles. So if you have a spinning object, the angular momentum is going to be equal to the rotational inertia and the rotational speed. So L is going to equal I omega, which is analogous to our linear momentum, P equals mv, where I is the same as m and omega is the same as v in the rotational quantity. Okay, let's look at a problem. We have a 4 kilogram object, so we know our mass is going to be 4 kilograms. It's moving in a circle of radius 8 meters, and we have a constant speed of 2 meters per second. You're asked for the angular momentum of the object with respect to an axis perpendicular to the circle and through the center. So L simply is mvr. We're given our mass to be 4 kilograms. We're given our speed to be 2 meters per second, and we're given our radius to be 8 meters. So L simply equals 64 kilograms meters squared per second. So that would be our angular momentum. Now, in this case, you're told you have a solid cylinder with a radius of 20 centimeters. So our radius is 20 centimeters, which we know we have to go to meters. So that's simply going to be 0.2 meters. We're told it has an angular velocity. So omega is 10 radians per second. And it has an angular momentum of 2 kilograms meters squared per second. And now you're asked to find the mass. So what is the mass? Well, we know that L equals I omega, right? Okay. So we know that we can rewrite this, and we can have that I is going to equal L over omega. So we have our L, which is our 2 kilograms meters squared per second, divided by our omega, which is 10 radians per second. So that's going to be 0.2 kilograms meters squared. So we're told it's a cylinder. So we know in terms of a cylinder, I equals 1/2 mr squared. And our problem asks us to find the mass. So we're going to rearrange this equation and solve it for mass. So when we do that, we're going to get our mass is equal to 2 over r squared times I. So therefore, our mass is going to equal 2 divided by 0.2 meters squared times I, which is 0.2 kilograms meters squared. So our meter squares are going to cancel in terms of units, and we get our answer in kilograms, which is going to be our mass. So you see, we had to take a couple different steps. First, we had to calculate what I was, and then we had to go back and look up what I is for a solid cylinder, so then we could pull out the mass and find that value, what we were asked. Okay, just like we had conservation of linear momentum, we also have conservation of angular momentum, which tells us that the angular momentum of a rotating object subject to no net external force, or no net external torque, is a constant. The final angular momentum must equal the linear angular momentum. So we have I omega final equals I omega initial. So just like we talked about conservation of linear momentum, the difference is that that interaction that changes the angular momentum is a torque rather than a force. So if no net external torque, if the external torque on the system is 0, then the angular momentum of that system doesn't change. And you can see this in example of a figure skater. So when she has a large moment of inertia, her arms are extended, she spins slow. When she pulls them in, she's going to do a faster spin. Now, our conservation of angular momentum, we note that the net external force doesn't need to be zero for the angular momentum to be conserved. So a net external force can be acting on the system as long as the forces don't produce a torque. And this is what we see for projectile motion, because force of gravity can be considered to act at the object's center of mass. Like linear momentum, angular momentum is also a vector quantity. So whenever you have conservation of a vector quantity, that means both your magnitude and direction are constant. Okay, let's look at another problem we have here. So we have a 500 kilogram merry-go-round. So we're going to put M of our merry is 500 kilograms. And it goes around with a radius of our merry-go-round is 2 meters. It's spinning at 2 radians per second. So omega is going to be 2 radians per second. A boy with a mass of 40 kilograms. So we have the mass of the boy, jumps on the outer rim. What's the new angular speed? So this 2 is our initial. We don't know what our final speed is. And we're told that I is going to be 1/2 mr squared. Okay. So we're going to have our initial, so our final equal our initial. So I final omega final is going to equal I initial omega initial. So now keep in mind, we're having the boy jump on. So initially we have this merry-go-round. We're told that I equals 1/2 mr squared. And we're told what our initial speed is, and that is 2 radians per second. Now, finally, we have the moment of inertia, which we have is 1/2 mr squared, plus we have to have the moment of inertia of our boy, which is mbr squared. And that's going to be times our omega f. Okay, so we have on this side, we're having our 1,000 kilograms meters squared times 2 radians per second. And then on this side, we have our 1,000 kilograms meters squared, plus we now have the boy, which is 160 kilograms meters squared. Okay. So all we have to do then is solve this for, oh, and this is multiplied by omega f. So then all we're doing is solving this equation for omega f. So we're going to divide both sides by 1,000 plus 160 kilograms meters squared. And our omega f is going to come out to be 1.7 radians per second. Right? And the reason that we had to add the boy to it was because in the final state, the boy is actually jumping on the merry-go-round. Okay, and let's do our last sample problem in chapter 8. So in this one, we have a horizontal disk of rotational inertia, 4.25 kilograms meters squared. So rotational inertia, 4.25 kilograms meters squared, with respect to its axis of symmetry, is spinning counterclockwise about its axis of symmetry as viewed from above at 15.5 revolutions per second on a frictionless, massless bearing. So first we have that. So our omega 1 is going to be 15.5 revolutions per second. So we want to go ahead and convert that to radians. So 2 pi radians in 1 revolution. And that's going to give us 97.39 radians per second. And then we have a second disk. So we have I2 has a rotational inertia of 1.80 kilograms meters squared with respect to its axis of symmetry, and it is spinning clockwise. So we know that's a negative value. Okay. At 14.2 revolutions per second. So omega 2 is going to be 14.2 revolutions per second. So again, we're going to convert that to 2 pi to radians, with 2 pi radians is 1 revolution. And that's going to give us 89.22 radians per second. It's dropped on top of the first. So the second disk is dropped on top of the first. The two disks stick together and rotate as one about their common axis of symmetry. At what new angular velocity in units of radians per second? So here we have the situation where we have our I1 omega 1 plus I2 omega 2 initially is going to equal the final situation where we have I1 plus I2, and now they're stuck together, so they rotate, they're stuck together, so they have a common speed, omega prime. So we need to solve this equation for omega prime. So what we're doing is we have, we'll come down here, we have our 4.25 kilograms meters squared times 97.39 radians per second plus I2 is negative 1.80 kilograms meters squared times 89.22 radians per second. And that's going to equal I1, which is 4.25 kilograms meters second, plus a negative 1.80 kilograms meters squared, and that's multiplied by our omega prime. Okay, so simplifying these, we get 413.91 kilograms meters squared radians per second, plus we have a negative 160.60 kilograms meters squared radians per second, and that equals 2.45 kilograms meters squared times omega prime. Okay, and then all we have to do now is solve for omega prime, and that's going to give us an answer of 103.4 radians per second. So just like we did when we had a collision in the translational sense that stuck together, we can have the same thing in the rotational sense. Okay, that is the end of chapter 8.